Hi, I'm Patrick Cannon, a research scientist at Improbable. This talk is a brief overview of some recent work incorporating ideas from generalized Bayesian inference into approximate Bayesian computation. It's joint work with one of my colleagues at Improbable, Sebastian Schmorn, and Jeremy Knoblauch from Warwick and the ATI. In our work, we often find that simulators provide only a partial picture of real-world processes. In order to use ABC when simulators aren't fully accurate representations of reality, we carried out this work to better understand the use of ABC in misspecified settings. We do this here in 3 steps. First, we reinterpret approximate Bayesian computation as not an approximation at all, but an instance of exact Bayesian inference in the presence of an implicitly defined error model. The second step is to show that these ABC posteriors are in fact a subset of generalized Bayesian posteriors, which gives a new motivation for viewing ABC as an exact algorithm. And finally, we use this new perspective to make some suggestions about how we can choose ABC kernels that more naturally reflect measurement error and are more robust to misspecification. We consider a simulator f parameterized by some vector theta, and we assume that the likelihood function isn't available analytically, so simulation-based inference. We have some observations y, drawn from the true data generating process p star, which is assumed to be unknown. And we're assuming that the simulator f is misspecified. So f isn't equal to p star for any value of theta, though we do assume that there exists a measurement error model g satisfying the given equation. Model misspecification naturally occurs in large-scale simulations. On screen now is an example of a model that we've worked on recently. It's an agent-based model for the pandemic, simulating every individual in the county of Devon in the UK. Such a model is naturally misspecified. ABC is normally applied as follows. You choose some probability kernel k, along with summary statistics eta. And then a single weighted sample is generated by first sampling a parameter theta from the prior distribution, then sampling a realization xi of the simulator conditional on theta I, and finally calculating the weight, which is whatever kernel was chosen applied to the norm of the difference of the summary stats. The algorithm just described induces an augmented distribution over theta and x, given in equation 1. A marginal of this distribution is given in equation 2 and is sometimes called the ABC posterior. The typical justification for the use of ABC in simulation-based inference is as the bandwidth h shrinks to 0, the kernel in equation 1 approaches a Dirac delta. And then the ABC posterior in equation 2 approaches the Bayesian posterior. However, we want to move away from this view. Ideally, we would use the true model error as the ABC kernel, but in practice, you don't know it. So you need to replace it with something simple and robust. And this leads us naturally to the idea of generalized Bayesian inference, which is a framework for extending the logic of Bayesian belief updating from likelihood functions to arbitrary loss functions. In particular, it can be shown that in such a framework, coherent belief updates follow the form given in equation 3, which should look familiar. Choosing w to be 1 and the loss to be the negative logarithm of the ABC kernel recovers the ABC posterior from the previous slide. So it's clear that ABC posteriors of the form we describe here are a subset of generalized Bayesian posteriors. One question this raises is, does this new lens change how we see traditional ABC kernel choices? The answer is a resounding yes. In particular, hard threshold kernels, a popular choice with ABC practitioners, are far less appealing when described as uniform noise models, which would in most modeling scenarios be an unconventional choice. In summary then, this generalized view offers a simple and principled justification for embracing loss functions in ABC that would otherwise be difficult to justify. More broadly, it leads us away from viewing ABC as a necessary evil and towards embracing it as a convincing robustification strategy in its own right. Many existing ABC strategies fit into this framework. Let's take a look at some of these applied to a simple toy example. We compare a typical ABC type loss to 2 losses which don't make use of summary statistics here. The first algorithm we call soft threshold ABC, which takes as its loss the squared norm of a difference of summary stats. For the toy example, we take the sample mean and variance, which are sufficient in this case. The second loss function we consider is a maximum mean discrepancy estimate, and this comes from the 2016 K2 ABC paper by Park et al. And the final loss function we consider is a Wasserstein distance, and this is related to the approach in the Bunton et al. 2019 paper. More details can be found in our paper, but On a high level, we show experimentally that the kind of loss functions inspired by the generalized approach can have both efficiency and robustness benefits. The plot shown here probes the performance of the algorithms under misspecification of the simulator, with misspecification increasing from left to right. It shows that there are ways of making soft threshold ABC approaches more robust through averaging, but that for a fraction of the computational cost, K2 and Wasserstein algorithms offer better performance under misspecification. Thanks for listening.